Vanessa and I welcome everyone to our talk about returning your GC system to its best performance, whether the system has been turned off for months or just not working the best. If the system has been off or the background of the chromatograms just don't look right, now is a good time to look at the gas clean filter. When was the last time you changed it, and have you looked at the indicator colors recently? Also, when was the last time you changed the syringe and wash vials, or changed out the wash solvent in those vials? Hopefully there aren't crystals or piece of septa floating in the wash vial waiting to clog the syringe or contaminate your samples. It's a good habit to track the number of injections on the syringe and also to check if the wash vials have any particles in them. Empty and wipe out the wash vials and fill with a new solvent regularly. And then it's a good habit to replace those every few months or once a year. Additionally, what color is your pump oil if you're using an oil rough pump? Or have you replaced the tip seals recently on your scroll pump? Or has it been a year or more? We're going to touch on each of these parts and more throughout this presentation. First, let's talk about clean gases and if a spent gas filter really affects your chromatography. We ran an experiment with our house-grade helium and a spent gas clean filter and monitored several ions, of which 32 mass to charge ratio, oxygen, was one of them. Oxygen can destroy the stationary phase on a column and shorten filament lifetime of a mass spectrometer, so it's best to try and keep the oxygen level as low as possible. While this extracted ion chromatogram doesn't look too bad with abundances around 34,000 counts, could it get even lower with a new filter? And we're going to answer that in a couple of slides. And I think we all know that it's best to change those filters when you see the indicators change, but if you're like me, you tend to tuck the gas clean filter almost out of sight next to or behind the GC and forget to look at the indicators regularly. With the gas clean sensor on the 8890 GC or Intuvo GC, a warning appears in the Diagnostics tab, even if the sensor is outside of your line of sight. When you start to see the light green indicator for oxygen turn a dark gray, as shown here, it's time to change the filter. Or with the gas clean sensor, you'll see the light on the sensor turn from green to yellow, and a diagnostic warning will pop up on your screen that either the oxygen or moisture indicator is saturated based on the indicator color. In this case, we're saying oxygen has saturated. This warning will not shut down a sequence, but it will cause just a diagnostic warning, as shown on our screen. So replacing your gas clean filter is easy to do, and you complete this with the normal steps with or without the sensor. If you're using the sensor on the 8890 or Intuvo GCs, you can follow the prompts on screen to step through the replacement of the filter. For those systems, the user can select View Conditions, and the system will ask you if you want to change the filter. Then the GC will make sure all zones are cool and walk you through the familiar steps of replacing the filter, of removing the ring, the old filter, installing new filter straight down onto the base, and tightening the ring back onto the base plate. And then you reinstall the gas clean sensor. So these GC systems will even ask if you want it to purge the gas clean filter for you. And the answer is yes, because the GC will automatically change the inlet to split injection and increase the flow to 400 mils per minute to purge the nitrogen out of the filter for 4 minutes. So let's go back to our gas filter experiment. When we install the new filter, allow it to purge, and then ran the background isothermal runs, we observed a drop in the oxygen mass to charge ratio of 32 by a factor of 3 compared to running with a spent filter. And that's even with high quality gas. Getting the oxygen as low as possible will help maintain a longer lifetime of the column and filaments, along with maintaining better peak shapes. It's always important to remember the rough pumps that pull vacuum in the mass spectrometer or chemiluminescence detectors, and those rough pumps do require some maintenance. Remember to change pump oil at least every 6 months if using oil-based pumps. If the oil goes in clear, the pump will run well, but black, thick oil can seize the pump and cause it to fail, leading to longer instrument downtime and expense, especially if the pump can't be fixed with new oil and you have to order a new pump. For some analyses, such as work with the sulfur chemiluminescence detector, it may be useful to change the oil every quarter or just more often than every 6 months. For scroll pumps, the tip seals should be replaced once a year and potentially more often for a very wet analysis. Just because these pumps tend to sit on the floor and out of view doesn't mean we can neglect them. Now I'm going to hand the presentation off to Vanessa.
When restarting your GC, don't forget to look under the covers of the instrument as well. If your inlet has been exposed to atmosphere for an extended period of time, it's probably a good time to change out your liner. I know when I'm planning on shutting down my GC for an extended period of time, I don't usually take out the liner, and occasionally I forget about the last dirty sample I ran before the shutdown. As part of my own operating procedure, I like to install a new liner before restarting my system so that I know I'm starting off with a fresh and clean liner. If the liner was exposed to atmosphere for an extended period of time, who knows what compounds could have drifted by my GC and into my liner while it was off. And if your GC was off and your column was still installed in your oven, you have to consider what the consequences will be for that column being exposed to the atmosphere. You may only need to recondition the column for a bit, but if doing normal front-end maintenance isn't getting your QC back to where it should be, then you may want to consider changing the column. These are just the parts that are easy to see, and we normally remember to change. There are also other parts, like the split vent trap, that should be considered. The split vent trap is located just behind the inlets, and you only need your thumb strength to open it up and swap them out. These traps should be replaced at least every year, or sometimes more frequently depending on your split ratio and how dirty your samples are. If you take out your split vent trap and it looks like this, all brown and grody, you may want to replace your split vent line too, as these particulates are probably hanging out in your split line and will create some crazy ghost peaks for you. And lastly, don't forget to look under the cover of your mass spec. I know it's scary to do if you've never taken off the covers of a mass spec, but I promise you can do this, and it's not that hard to do. Check out the fan. It's situated just below your PFTBA valve, and it will collect dust no matter how clean you think your lab is. And that dust can cause your fan to work harder than it needs to in order to keep your mass spec running. And when too much dust clogs up your fan, it will blow a board, and then you will have to wait until your friendly neighborhood FSC can stop by and swap it out for you. It's like a hairdryer. Every once in a while, you have to clean out that back part, or else it will overheat, and then you'll end up with frizzy hair. And before you start out your GCMS back up, it's the perfect time to make sure that our system is ready to get started, because we don't want to turn it on only to have avoidable issues later, and then we'll really be pulling our hair out. How do you know if your system is ready to run? Here's a chromatogram of a standard injection on a system that has been off for 1 week. It looks like most of the peaks are present, but there is an increase in the baseline toward the end of the run. If you aren't sure if your chromatogram looks okay, the best thing to do is to compare this injection with the previous run from before the GC was shut down. When we compare the tick of the system after it had been open for 1 week to one from November, when it had been under vacuum for a long time, you can see that the response is 10 times lower for the open system, and it appears that we are not seeing some critical peaks. If you aren't sure if you should replace the column, liner, or septum to get your sensitivity back, first think about what will be the easiest and fastest thing to do, and go from there. Changing the septum and liner will always be the fastest things you can do, since you don't need to wait for your inlet to cool down. Changing the gold seal is also a relatively quick maintenance, but you do want to wait a bit for the inlet to cool down first. Changing the column can take a long time since you have to properly vent and cool down your system. So first try reconditioning your column and see if your baseline decreases after an hour of conditioning. If the baseline does not decrease, then it would be necessary to change the column. And when you are changing a column, it's good practice to start with a fresh liner, septum, and gold seal. And you can see that once this was done, our response not only returned, but has also improved. When you need to replace your column, it's important to do it the right way. GCMS systems are not like light switches, and if you just flip off the power, you can eventually run into issues with electronic boards, which is why it's important to follow the proper process when shutting down your GCMS to change a column. With a mass spec, the first thing you should do is vent your system. The best way to do this is from the tune and vacuum control screen in ChemStation or Mass Hunter Acquisition. The vent cycle takes about 30 to 45 minutes to complete. If you have an atmospheric detector, set the detector temperature to ambient. And at this time, I also like to set my injector temperature to ambient as well. Once your mass spec has completed the vent cycle, turn it off. Also verify that your rough pump has turned off too. Most of the time, the pump is plugged directly into your mass spec, which is how it gets power, so it should turn off when you shut down your mass spec. But I still like to verify that it's off. Now set your oven to ambient temperature and turn off your gas flow. You can turn off your oven if you like, but it's not necessary. And some people also like to turn off their GC as well, but you don't have to so long as your temperatures are set to ambient and you turn off your gas flows. And finally, on your mass spec, open up the vent valve. And now you're ready to remove your column. When we are ready to install our new column, it's important to have the proper depth of column going into the inlet. Depending on the inlet you are using, there is an optimum column length for the inlet. The optimum length for a column with an Agilent splitless inlet is 4 to 6 millimeters above the ferrule. For multimode inlets, also known as MMI, the optimum length of column above the ferrule is 12 to 14 millimeters. This is why the length of the column going into your inlet matters. Here we can see exactly what is happening in our inlet. See how the column is sticking up into the bottom of the liner? This is what we want. The tip of our column entering the bottom of the liner, but not so far up that it passes the taper. If our column was too low or too high, it will negatively affect the transfer of our vaporized sample onto the column and will lead to thermal discrimination. Here's what that thermal discrimination looks like on a multimode inlet and why it's important to be precise when installing your column. We injected a mixture of alkanes with a range of C10 to C44 on an MMI inlet while only changing the length of column above the ferrule, looking at 10 millimeters up to 16 millimeters of column above the ferrule at 2 millimeter increments. At 12 millimeter extension past the ferrule, the end of the column is 2/3 of the way up the end of the cone at the bottom of the single taper splitless liner. 10 millimeter extension would put the end near the bottom of the cone, and we would start to see a loss of response for our heavier alkanes. A new tool that we have can make installing your column into your inlet and detector much easier. One complaint that we always get is that it can be hard to keep the column length above the ferrule at the right position as you install it. Everyone is always afraid that it will move during installation and then it will end up either too high, too low, or sometimes fall out of the bottom of the nut. I've seen some people use a used septum below the bottom of the nut to try and hold it into place, but this isn't a great idea since it can create another thermal zone in the path length of the column. Before I was able to figure out the best grip for me holding the column into place, I used to take a septum and make a slice in it so that way I could do the same septum trick but still remove it after I installed it. But sometimes my column would still slide if I cut the septum too much, or it would get stuck on the column if I didn't cut it enough. We came out with the self-tightening column nut a while ago, which makes column installation much easier, as you don't need any tools, and you can use the same graphite polyamide ferrule on both the mass spec and the inlet self-tightening nuts. And since there is a spring-driven piston design, it continuously presses against the ferrule, so you don't have to retighten it after thermal cycling. But customers still asked about how to best hold the column into place during installation. So we made an adjustment to our self-tightening column nuts. We added a collar that can be tightened to hold the column into place, and then easily removed after installation. With the addition of the collar, you can easily set the depth of the column for the inlet or detector. Tighten the collar into place, install it, and then remove the collar and your system is ready to run. Just as it's important to set the depth of column going into the inlet, it is also important to set the depth of column going into your detector as well. The depth varies for each detector and is based on what the optimum length is. To help with getting the right depth of column going into the mass spec, we have a handy tool that mimics the length of the transfer line. Depending on your ionization source, if you are using a standard inert source, you would want that column to extend 1 to 2 millimeters past the end of the tool, and 5 millimeters for a high efficiency source to achieve optimum ionization. Just like there is a proper way to shut down your mass spec, there is also a proper way to turn everything back on. First, close the vent valve on your mass spec. If you will forget to do this, you'll hear a hissing sound and your mass spec won't pump down. Second, turn on your mass spec. If your pump is connected directly to your mass spec, it should kick on right away and your system will start to pump down. You may need to gently push against the analyzer door at the beginning, but once the pump kicks on, it will pull the door closed for you. If this doesn't happen in the first 30 seconds of turning on your mass spec, turn it off right away. There may be an O-ring blocking the analyzer door from closing or a cord in the way. Locate the source of the blockage and fix it, and then turn on your mass spec. Listen for the sound of the turbo pump kicking on. It will sound like an airplane taking off, and this means that your mass spec is starting up. This is normal, and usually when I open up my instrument control software. Apply the set temperatures to your quads and your ion source and make sure that everything appears to be communicating properly. Now you can turn on your column flow and make sure that you don't have any big leaks before turning up the temperature of your inlet and detectors. From the tune and vacuum control screen, you can initiate a pump down, and once the pump speed and heaters have reached our set temperatures, you can then bake out the source. The temperature and length of time needed for a bakeout will be dependent on how long the system has been off, the temperature conditions in the lab, and the maximum temperature of your source, which Angie will talk about later. A good rule of thumb for bakeouts I like to follow is always about 2 hours and slightly higher than I'm planning on running my source at. If you're in a humid environment or your mass spec has been off for an extended period of time, you may need to bake out your source for longer. But you can always start with 2 hours for a bakeout and then do an additional bakeout if needed. Once the bakeout is completed, take a look at your vacuum gauge. For an electron impact or EI source, a good range of high vacuum would be between 4.0 times 10 to the negative 5 to 8.0 times 10 to the negative 5 torr. If your vacuum is not in this range, there could be a leak or a problem with the turbo pump. You can always compare your current vacuum to a previous setting by comparing your current vacuum to a previous tune. And you can always run an air and water check to see if your system is ready to run. We usually say to make sure your water, nitrogen, and oxygen levels are below 10%, but I would argue that you actually want them to be less than about 4% to make sure that your phases of your column are protected. Because when oxygen and heat interact with column phase, bad things will happen. If needed, slightly tighten the self-tightening column nut just a little more until your air and water values are where they should be. And please don't use a wrench or any tools on the self-tightening column nut. This is how strip transfer lines happen. And once your air and water percentage are below 4%, you can now condition the column. Once your system is leak-free, it's important to condition your column. The time it takes and the temperature at which you will condition is going to vary depending on the phase of the column you are using and the maximum temperature you are planning on operating at. What I like to do is take my column up to the maximum temperature I need without going above the maximum temperature stated on the box with the gas flow on and hold it there for an hour or two. The column is deemed conditioned when the baseline is flat and no longer decreases, which is easy to see on an FID. This is a conditioning profile for a DB5HT column that I condition at 380 degrees for just over 2 hours. The DB5HT column is on special high-temperature fused silica, which can be taken up to 400 degrees Celsius. But regular fused silica should not be taken above 350 degrees due to temperature limits of traditional polyamide fused silica columns. You can see an initial jump in the baseline as the column is first taken up to temperature, but then it decreases and levels out around 100 minutes at 380 degrees Celsius. This is when I would say that the column is conditioned and ready to run. If you don't need to operate at the maximum temperature of your column, there is no need to condition at that column's phase's max temperature, and conditioning time may be much less than 1 or 2 hours.